Yes, there have been, it's a time for, I guess, seems like there's a lot of concessions, retrospection, a little bit of recrimination. But of course, it's important to go forward since it's the beginning. What I'm going to talk about is a novel architecture that is continued to add to the ideas of scaling. And it is using an unusual approach that is nonetheless easy to present. And we will show what its utility, what we think its utility is. I'm speaking, but the people who actually built this are joining the witness and Owen. LLMs, of course, are spectacular, but they can make, as we know, highly inventive errors. There's an argument about their internal representations, and it's going to go up over and over again today, so I'll elide over it. But they are expensive in terms, especially of power budgets, and by power budgets, I literally mean things like hydroelectric plants, which are, of course, where almost all of the server farms for all of the companies working on these tasks are. One of the, when we talk about scaling, a lot of what we're talking about is the software side of it and the compression side of it, but it is interesting to note the sheer expense of each of the steps. The thing I'm going to focus on to some extent is the fact that LLMs are a new set of methods that are based on ancient methods. The operations that LLMs are carrying out are being built out of things like backprop and they don't need to be. And this is I think just simple examples of things like embedding, which of course are being done by backprop association by and large, which is very expensive and not needed for unsupervised tasks. And for a non-deep learning operation, I use deep learning. An incipient question that will be coming up for LLMs will be to what extent can we do them with other kinds of methods. And yes, this was simply to say, yes, you can build a computer out of different tools and Legos. So if you don't use these methods, what do you use? Well, we know that we have other embedding methods like contrastive embedding. And there is a lot we can do with the so-called attention mechanisms, and I'm going to simply show you an approach that is using the new approach that's using really low computational cost and bypasses the now relevant approach. Yeah. Is it going now?
Yes.
Lovely, thank you. Good. So, I'm going to focus on what I think of as underexplored mechanisms, mainly very low precision components that we can build up into high precision operations, extreme sparsity, and a number of other related findings, with resulting properties that I'll demonstrate. Some of which I'll simply search. That these things lend themselves to hardware. They build automatically from the primitives. They build relations, things like particle, and they are generative and compositional. So, quick overview of what I'm going to do. I'm just going to quickly introduce the particle approach. I'm going to introduce the Hamiltonians, which is from the title, how they work. I'm going to go step by step through how to actually build these things, just so none of it's mysterious, so that it's a clear, simple step by step approach. And then I'm going to show how these things build arbitrary sized hierarchies they certainly look symbolic. And to show you the kinds of representations, rich representations that they build. And then I'm going to contrast these representations with that. So over to you first. Standard approaches forever using the same using extremely related methods. What we're going to do is really an approach that from the bottom level is quite different. So you take a little piece of, I'm just going to start with things like MS for example. There's nothing to do with MS. Take a little chunk of this thing and look inside it, and we've got our little binary relations. And those little binary relations, there are simple on versus off, and there are possible edges, showing the set of possible edges that we can have for these. But we'll just focus on the four simplest ones from which everything else can be composed. The simple pairs or one. And we build up parts from these. Again, I'm doing this on MS, but I'm going to show you a whole bunch of other examples coming up. So we take these pieces, these tiny little pairwise relations of on, off, and input a graph for the entire state. Produce a Hamiltonian, which I'll show you exactly how we do it. Very straightforward. Generate an energy measure from state and the Hamiltonian, and the state is, whatever it is, more or less recognized the lower the energy is. So it's a standard energy based approach. So what you want is something that's down low in the energy for these state configurations. What I'm not going to show you is how to build those Hamiltonians, how to composite them, and then you'll have a boots on the ground feel for what we're actually doing. So for each of these mechanisms, we've got a simple, as I showed, energy calculation, and that energy calculation is a standard Hamiltonian formulation from standard things in math or physics. And of course, you could solve this thing, and what you do is you solve it to get the contents A, B, C that are going to be in the Hamiltonian for each of these relations. And the characteristics of this will be, as we'll see, they're extremely low precision. They're using nothing but binary arithmetic. They are compositional, so even though they're extremely simple at this level, they can build up to arbitrary size. They have intrinsic, if you will, logic kinds of relations to them, and they naturally, almost intuitively here, lend themselves to algorithms. So for each of the XY pairs, we can, of course, solve this to find what the Hamiltonians are. Here are the four for these guys. And the thing that makes it work, if you will, is the fact that once you've got these, which we got by no mysterious process, just by solving this, you can now run this equation, find the energy on these things, and do matches. So you're doing an extremely inexpensive process to generate matches for arbitrary inputs. So take now a graph. So instead of just a single pair, I'm going to just show a simple, the tiniest little example that I can show of compositionality, composing these things. How do they compose? There's a convention for how you read these. One, this guy 1, 1, 0, 0. That's the vector that we use. And now what I'm going to do is find the appropriate relations for each of these. You can see which ones they are in the network for each of the edges. And now I'm going to show you. Okay, we've got each of these edges. As you've got there, I've got the color for this. Now what we want is the composition. Put together the Hamiltonian for this entire thing. It's very simple. It's going to be a 4x4 now, instead of a 2x2 or 2x2 Hamiltonian. And all you're doing is taking the ones in each of the spots that they belong in the graph and sticking their Hamiltonian into the composite Hamiltonian, and keep finding each one, add it into where it belongs in the Hamiltonian. Again, where it belongs in the Hamiltonian. Again, where it belongs. And finally, we've got the complete Hamiltonian, which we compute, and you get the product. So the compositionality of it is incredibly straightforward. And again, no very low precision. We're using, I mean, it's perfectly high precision. It's all the precision we need for this, but it's using very, very cheap operations. Now we can use this, and just going to do a simple match example. So we've got one graph, we've got another graph, and you run now the energy calculation on this new graph, having trained on the previous. So it's testing on this beta thing, having trained on alpha, and what you're going to get if you just do the arithmetic is you'll get something that's non-zero, greater than zero, and it'll be rejected. So we make a whole bunch of composite matches in this fashion, and I'm showing you this is a scare slide to show you you can do arbitrary calculations this time. Now what I'm going to show you is what do you build? Obviously, the low-level version of it is not the interesting thing, except for the fact that you can do everything with that low-level version. We will do it now on arbitrary domains. Here is just another standard kind of ancient neural network thing, credit application. You take the features, and those features now, here are the features around the edges of this thing, and you can make arbitrary pairs. So there's no more topography in the thing. You can make arbitrary pairs across the input, the data, and each of those pairs can then be learned as one of these HNet pairs. So now you're building up little sets of these things, and you can composite them into higher level examples of what is in the graph. But now the graph is not a MNIST type topographic graph, it's an arbitrary set of data. And you build arbitrary hierarchies out of these things. I'm showing you a pretty shallow one, but you can see that they can build to arbitrary size. And of course, these lend themselves to the kinds of things that LLMs are already extremely good at, like explanations. It's showing you what the relations are in the data that are giving you the things that you're recognizing and therefore explaining. A minor proposed effect from this is just simple boosting. In general, what you want for this is just a cartoon first for classification accuracy with classifier alone and the classifier with these rich representations. And indeed, this is exactly what it does. So if you use just an SVM on the raw data, it'll get you whatever 70%. And if you use an HNet first and then the SVM as a back end, you get improved classification accuracy. What's intriguing about this is now the back end, the gradient descent piece, is a tiny sliver of that. It's a very, very cheap little operation. So you offloaded all the real computation onto these very inexpensive primitives. Interestingly, you can build, you can recognize across, because you're building these hierarchies and heteroarchies, you can recognize parts that happen to occur in more than one kind of element. I'm showing them an MNIST again, just because they're easy to see. So you've got a cap on a 2 and on an 8, and on certain kinds of 6s. And you've got other examples of things that are discriminative, like the middles of these things. So a 2 and an 8 both share a cap, but they have different middles to them. And so you're learning these discriminative, contrasted, if you will, categories that are just parts of the data, not the data overall. So the partial is working with it. The abductive steps that you can now do on this are to generalize. You can now I'll show you an example, but I'm just going to quickly say it out loud. You can produce initial frames and overgeneralize. That is, make incorrect overgeneralizations, which you can then use for predictive inference, and then match and mismatch on those to find exceptions, which you then continue to learn. So, for example, in the standard clever task, got a bunch of objects, and we can, the front ends can learn these the little parts to these things. Now the relations between the parts are being learned, and those relations become an abstraction, and we can make arbitrary relations that are learned as relation types, just like I showed you the cap to the 2 and the cap to the 8. These are the same kinds of terms. We're seeing the kinds of parts that co-occur across different data. So, for instance, now we can train it on in clever faces, which we just created ourselves in clever, and non-faces, and back not to Winograd, but to patents, and showing the system the things that work for it and the things that don't. And initially, what it will do is we'll build up loads and loads and loads of pairs of the kinds of relations. There it is. The kinds of relations that can occur, and then the overgeneralization step, calling the abductive step, is to pare these down to say, oh no, all of them have to have these up here, this here, and this down here. Now, this is a great overgeneralization. Good. Let me write on an enormous overgeneralization, and it will have to learn exceptions, and that kind of exception. The man ran, the man runned, which a kid will learn before he learns the man ran, is creating a top-down frame, if you will, and then using that to generate predictions, which it then makes viable exceptions. All I want to do now is just compare and contrast some of these architectures. Well, and I should have mentioned everything that I somewhere on one of the slides, and I think at the end I have a website where all this is GitHub. The characteristics of, say, CNN are, and they exhibit dense connectivity, high precision operations where every wave tends to have a certain number of bits in it. What this network is doing something really not related to this. It's building these particle edge representations. It's building those into what you can think of as tier 1 components, using those to build high level edge representations, edges of edges, if you will, sequences of sequences, which become tier 2 components, etc. At any point, notice this is all unsupervised. At any point, you can easily put in some little gradient descent thing, and now it's cheap. Now all you need is a tiny sliver of gradient descent. It's not doing the heavy lifting anymore. And the reason that that's probably a reasonable idea is because that's the expensive piece. Whereas these things are extremely inexpensive. And then finding the results. These exhibit very sparse connectivity and activations and very, as we've seen, low precision operations. And I will just briefly say there also are corresponding architectural features, which we think is very interesting. There are ways of translating the operations that we're talking about to standard linear algebra type neural networks. So we can show exactly what those correspondences are, and that's in the paper. Interestingly, if you did the corresponding linear algebra version, you would be doing the expensive thing. By doing it this way, you're doing it the cheap way, cheap but not dirty way, and you still get, by doing the corresponding version, you still get the full compositionality of it. So again, we can directly relate these things to standard neural networks, and we can show what the characteristics of them are, which we think is a useful way of understanding their data. And all I'm going to do now is say that give you a quick summary. These things are building arbitrary relations at the lowest level. They're not building arbitrary relations way up high down your at the very end of a deep learning pathway or an LLM pathway. Rather, they have little simple logic operations on arbitrary relations at the lowest level. They readily build particle hierarchies there. It's like they're made to. And it's a clear trade-off of putting in lots of space, storing all these little things for a very low time complexity. And the things that you're storing in space are extremely cheap. They're binary pairs. This lends itself to hardware. So the weights now have to be low precision. The whole thing is, of course, incredibly intrinsically parallel, with lending itself to possible firmware level implementation. And all of it, you can easily use low power designs, as evidenced by the fact that they're in fact nanoways hardware that does this stuff. These things are actually being used to put into devices that, for instance, allow you to put low power processors onto remote sensors, as opposed to having to transmit information to a higher power data bus. And all of this is there's code and all of it. See, there we go. All of it is at this thing on GitHub, and that's also referred to in the paper. Yeah, absolutely on time. Thank you very much.
Any questions? What potential do you see with scaling this up for tasks that are more cognitively demanding? And have you done experiments in this regard?
We haven't done any big examples of any kind yet, and it's early days. We really are interested actually in potential collaborations. Anybody who's interested in playing with the thing, which is one of the reasons why we put it on GitHub, because it seems likely, just looking at the little systems that we've built already, that you can easily, I mean, they're just very naturally compose themselves, and so it's very easy to make hierarchies out of them. And the hierarchies that they build have these little logic operations in them, so that you can read them very straightforwardly. And it's easy to build a little system that looks at the none of the layers are hidden in that sense. Looks at the representations that are being built, and it's easy to read them out and see how it arrives at the conclusions that it does. We really want to build that out to large examples, and we think it lends itself to it. And none of that exists yet.
But is this system only able to output classification results, or can it also continuous results as well?
Oh, absolutely. So it will generate, it's doing an energy calculation. So it will generate just, lower energy for better matches and higher energy for worse matches. The only reason I'm even comparing it to that kind of operation is because we all know where those things plug into larger systems. And so we can think of this, just seemed easier as a way to think of it as just a wholesale substitute for things that we already understand well. And again, there is a formal analysis that shows the direct relationship between these things and what we can do, what you would do if you instead built them in standard neural network linear algebra. So yes, we think that these are applicable to, well, in principle, they should be applicable to anything that you could stick a backdrop into, anything that you could stick any simple neural network into. Yes.
So this may not be super well formed, but it looked like, when you're talking your hierarchies, you sort of have one layer and this is sort of next layer, next layer, next layer. When you also have a more flexible hierarchy structure there, so you have, some subset being summarized, directly to a higher layer and combining lower and higher layers.
Actually, yes, I think I had an example. I didn't go in detail enough on the diagrams, but yes, so any unit can itself be a node. And that node can be part of some higher level node, even if it's bypassing other structures that might be in between in some other arm of the hierarchy. That sounds like what you're asking.
Yeah, that's what I guess.
Yeah.
Some kind of combination of operators.
Right, right. And notice that there's a huge search space there. And so what you do is you generate a whole bunch of these. This is why we're doing the abduction stack, so that you can generate high level frames of these things and try to make predictive examples downward and have it fail. So that part of the training now is, again, it's a lot cheaper way to fail than when we're training our typical LLMs, but it will fail, and then you use that to give it counterexamples. And again, all of this can be done with unsupervised, non-gradient descent, clustering kinds of learning, like contrastive things.
That's great. Thank you
Cool.
very much.
Thank you.